of this circuit design and simulation marathon using eSim. So before we go ahead, let me just give a small brief about FOSSEE. So the FOSSEE project, FOSSEE stands for Free/Libre Open Source Software for Education. It promotes the use of FLOSS tools to improve the quality of education in our country. Our main aim is to reduce the dependency on proprietary software in educational institutions. Our FOSSEE project is a part of the National Mission on Education through Information and Communication Technology, Ministry of Education, Government of India. So let me begin the event by welcoming Professor Kannan Maudgalya. Professor Kannan is a faculty in the Department of Chemical Engineering, IIT Bombay, and Iraq and Meheru Mehta Advanced Education Technology Chair Professor. He is the principal investigator of the FOSSEE project. So I will now hand it over to Professor Kannan. Over to you, sir.
Yash, has Professor Sahasrabudhe joined?
Yes, sir. Anil sir has joined.
Yeah.
Good morning, Professor Sahasrabudhe.
Yeah, I'm here.
Namaskar, namaskar.
Namaskar, namaskar.
Okay, really delighted to have you. Let me see who else is here.
Ganesh has joined?
Ganesh, have you joined?
Yeah, I'm here.
Great. Happy to have you, Ganesh. Yeah. Yeah, late in the night. So what we will do is right after Professor Sahasrabudhe, we will let you talk and then you can go. Okay. Thanks.
Sure. Thanks.
So I have a presentation. I will give a brief overview of what we have done and so on. And then after that, I will hand over to back to Yash. So I want to first of all thank everybody, especially the students, for having joined in big numbers. 3,000 is not a small number. Really delighted to have you. Let me share the screen. Okay, you can see my screen, right? Yeah. So
yes, we can also see you have done some coding work at the background.
Yes, it's latex.
Yeah.
Yeah, my screen is generally desktop is messy, right?
Yes.
So I'm going to talk about this eSim. Why should you take it seriously? So I will take about somewhere between 5 to maybe 10 minutes max, just to give an overview of what we are doing and so on. So eSim is suitable for mixed signal simulation, and then it is released under GPL license. It's made from KiCad, ngSpice, and Ghdl. So just to give a background of what we did, this mixed signal simulation, in SPICE, you actually have XSPICE and digital simulation can be done. And so analog part is separated and then digital part is separated. And these are connected through an ADC and DAC. But it is somewhat difficult to use this XSPICE language for digital simulation. So what our team did was to replace this XSPICE with Ghdl using the same infrastructure. In fact, this work was overseen by Professor Madhav Desai, who will be joining us shortly. He will be joining from Spain. So he's the one who said that this is already there. Why don't we just take it out, put it outside, and do this in Ghdl and take it back. Now, anybody who knows Ghdl can include this, and so that can be interfaced with this. So after that, our team replaced Ghdl here with C code for microcontroller instructions. For example, here, previously we had Ghdl here. In the place of Ghdl, we have a microcontroller. So what it does is you can take a microcontroller and say that for every instruction, replace it with a C code. Then you have all other things, everything else is the same. Okay. So analog simulation is done in SPICE, and the digital simulation is done through ADC, DAC, to this, through this, eventually microcontroller simulation also. Okay. We wrote this as a paper eSim, an open source EDA tool for mixed signal and microcontroller simulations. This was in an IEEE conference that was held last month in, not even a month ago, in Malaysia. It's an IEEE paper. Here it is. You can see Saurabh Bansode, Rahul Patnikar. They are the people who actually developed some of these. Gloria also, you can see Professor Madhav Desai. Ashutosh Jha, he worked with us. He was a student at VIT Vellore, and he worked with us as an intern, a semester-long intern. We previously called eSim as OSCAD. In fact, we wrote a book. This book is available with us. We printed 9,000 copies of it for a workshop. The price was about 67 rupees or something like that. We distributed to workshop participants. And Cadence was not happy about our using the word OSCAD. You see, this was OSCAD. It sounded like ORCAD. So they requested us to change the name. So we changed the name to eSim. Promoting eSim. We have been promoting eSim in a big way. For example, we did a massive faculty training using. We conducted a coordinator workshop on 27 July 2019 and main workshop on 21st September. By the way, this was 2019, before the pandemic, for 3,200 college teachers simultaneously. Okay. I'm going to skip this. That would have been a nice one. But anyway, I don't want to waste time. That was a coordinator workshop. So the main workshop was conducted in 118 remote centers. You can see that Myanmar also is there, Burma. Actually, this workshop was received also in Myanmar. Okay, at that time, this was before the coup. So we can actually have a live interaction with the Myanmar people. You can just see this. A few words.
Thank you, Professor. Good grammar and spelling
Sorry
are
about
important,
this.
but if you want to write essays that inspire.
We at MIT are extremely privileged to be part of it. And today we have 25 participants from 6 universities here nearby Madrid region. The next time around when we participate, we'll move this venue.
Okay. So I'll skip that. In fact, this was the circuit that we used in that workshop. It is just a stable multivibrator circuit. And we have a colleague by name Professor Pramod, and he suggested that because many people don't even know what a simulator is for. So can we teach them? So this was the stable multivibrator circuit that we built. Together, it was about, I think, 47 rupees or something, delivered by FedEx in all the remote centers. Okay. Remember, 116 remote centers, 3,200 participants. Of course, to Myanmar, I took them myself. I had gone. So the participants had to do the simulation with on the software, and then create Gerber files and make PCB plus circuit and validate. But they also measured it on the circuit itself. And then they also check by hand calculation, because you can easily find the time of oscillation for this. Okay. In the past 7 to 8 years, we have trained 75,000 people in OSCAD, 10,000 people in eSim, 7 million people on all FOSS. In fact, we did a postal campaign. We sent a poster to 20,000 heads of departments that have circuit design. This poster was sent, actual printed poster was sent to 20,000 heads of departments, telling the students, build and simulate circuits, design PCBs, upload, earn money, win attractive prices, get certificates, get internship, improve job potential. We have 150 eSIM circuits created by students and 150 circuits migrated from PSpice and LTSpice. In fact, we have we had an intern by name Siddhant Ranade who wrote this converter from PSpice to eSIM. That is, somebody already has a legacy circuit in PSpice, then we can have it running in eSIM. Similarly, from LT Spice to eSim. By the way, these features are not available. Supposing you're using eSim, tomorrow you want to use PSpice, and you'll have to forego that. We don't have that. FOSSEE Fellowship, performance-based selection, registration, screening task, review, and then selection. I'm talking about the one that we sent 2020. 50,000 envelopes were sent to as many departments, 9,000 registered, 500 completed screening tasks, 250 found suitable. We took 100 as FOSSEE fellows for all topics. Some of them did eSim work. FOSSEE fellows created eSim on cloud. We are still working on that. Hopefully, we will release this also sometime. We collect high performers in our projects. We conduct job fairs for them. Example, we organized one with NASCOM. 10 companies participated. 30 students out of 40 who joined received 2 jobs each. In fact, they got 59 jobs in total. This thing is also missing. Unfortunately, I forgot to open it. It's an embedded video. Okay, I will play this shortly, but what time is it? We are running out of time. What we will do is, let me just finish what I said. So these videos, I'm going to skip, unfortunately. These job fairs are very good because lower ranked colleges have no campus placements. That's what that student Mayur says in that slide. Their students, especially toppers, suffer, whereas small companies have difficulty in recruiting in both high and low ranked colleges. Here is a comparison of eSim with commercial software. Okay, so we plan to do the same thing for people who work with us. We will already your things will be available. For example, let me see if I can. No, I don't have that, but I can show that here. Let me say eSim. This is our web page, circuit simulation project. And in that, completed circuits, for example, and this. You can see that various circuits created by students from across the country. These are all created by VIT students, MS Ramaiah, Don Bosco, St. Xavier's, then NIT Durgapur, and so on and so forth. IA, IIIT, Trichy, and so on and so forth. Each one has a circuit. If I click this, it'll say, what do you want to do? Download the code and things like that. Okay. So those are created by students, and the students get recognition. Some of them have got, in fact, one student got a job in internship in Cadence, and then later on he went to, I think, North Carolina State University, right? So it is actually very good for all the circuits that you create will be hosted here. Okay. Now here I'm comparing eSim with commercial software. So ORCAD, LT Spice, and eSim. PSpice comes as a part of ORCAD. You can see that things are very similar. There are only a few extra things. For example, Monte Carlo simulation can be done in ORCAD, whereas eSim cannot do, but all other things it can do. You can create a schematic entry. You can do PCB design. You can do SPICE simulation. And then user forums are there. Model editor is there. Only thing is to use the user forum, it is accessible to all of us. Anybody can come and ask questions. Whereas I'm not sure about ORCAD and LT Spice, whether they would want a license number. I also have some cost comparison. eSim is, of course, absolutely open source. Cost of Cadence suite. For colleges, it is most likely free. But for industry, for the entire suite, it costs approximately about $50,000 to $70,000 per year per user. So in other words, it may be free for you in the colleges, but if you go to company, even if it is a small company, you'll have to pay this. Now, what about students who go for, let's say, training in a training institution? It is $600 per student per month. This is what the company Cadence charges from the training institutions, whereas the training institutes charge students double the amount. Interestingly, NME ICT mission statement had ORCAD as a part of it. Okay, you can see this here. See this 319 adaptation. It was part of the mission statement. In fact, it is a cabinet approved document. NME ICT mission statement document was approved by the cabinet. The cabinet said adaptation and deployment of open source simulation packages like ORCAD, Scilab. Scilab was not spelled properly, but you can see MATLAB is mentioned, ORCAD is mentioned there. So ORCAD is something that we wanted to substitute with an open source equivalent. And in fact, when we did this, Mr. Sinha, who was the mission director, was very happy that we did this. So our project is funded by NME ICT, MOE, which was called MHRD at one time. So thank you. So I'm going to stop at this point, and I'm going to, let me see, stop share. And I'm going to hand over the mic back to Yash.
Thank you. Thank you so much, sir. Thank you so much. So now moving ahead, we move towards the inauguration of this marathon. So may I please invite Professor Anil Sahasrabudhe, AICTE Chairman, to inaugurate this marathon. Anil sir, can you please share your screen and click this link? I have sent it to you.
Okay, I think I have not checked the which ID it has been sent. You tell me.
Sir, I have just sent it on chat.
Huh?
Yeah, I have sent it to you on Zoom chat. If you can check the chat, I have sent it personally to you.
No, from which email ID you have sent?
No, he has put it on Zoom itself.
Zoom.
Oh, Zoom itself.
Yes, yes, sir.
So it's very easy for you.
Yes.
Where should I look it?
So there's an option chat in the
chat mein dala hai kya?
Yes, 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 sir. So you can share your screen, sir. You can share your screen and then open this link in the browser and click it. That's it.
Is it now visible?
Yes,
Yep.
sir. Yes, sir.
Yes.
So,
Sir, please click it. Please click it. It will be done, sir.
Okay.
so ribbon cut gaya.
So everybody, can you please unmute and just do a round applause for Professor Anil? Everybody, can you please unmute? Great, great.
Response. Okay. So thank you so much, sir. So
Yes, you are on mute.
Yes.
yeah, done, sir, done. Sorry. Yeah, thank you so much, Anil sir, for doing this. So now, since it is virtual, so this is a new way of doing it. So may I again please ask Anil sir to address our audience. Anil sir, can you please address the participants?
Yeah, thank you so much, Yash Vora, Kunal Ghosh, who started off in the beginning, and my good friend, Dr. Kunal Modgolia, who has been an inspiration all through for promoting FOSSI, all through the country. We have Ganesh, who has joined in the midnight, for attending this function, and all other students and faculty members who have joined for this very interesting and important circuit design and simulation marathon using eSim. I didn't know anything about it, and only through the short presentation which Dr. Kannan made just now, about 5 minutes ago, I could understand that we have combined XSpice GHDL into NGHDL, and even using C coding, you can move to and fro, and then you can control those microcontrollers. And these are very, very important tools for designing circuit and simulation. We have both analog as well as digital, circuits being designed. I heard about FPGA earlier and many other such tools which are coming in. We must train our students, and we had association between AICT and IIT Bombay's FOSSI lab in a variety of ways in the past, in the last 1 year in pandemic itself, whether it is the starting of what we call the stories of Panchatantra, being created as films, short films, And school children participated in that, fourth standard, fifth standard, and they learned the open source software and created excellent, interesting, stories about our own ancient, stories which we all studied, either in the Chanda Mama or in Panchatantra. They were recreated in the form of a video. And that is so exciting, students being able to do that. And we involved Whistling Woods also in that. This is one of the institutions who run for entire filmmaking. When people will look at all of this, their interest, enthusiasm, excitement has no bounds. And similarly, we then had some kind of an hackathon with ISRO, and it was called Mapathon. And again, using a lot of GIS tools and ISRO maps, how each district's resources can be mapped, different layers can be created, which will be very useful in terms of peacetime as well as crisis time. Whether it is in terms of pandemic, want to know where are the hospitals, where are the ambulances available, all of that can be together, brought in. Even other economic aspects like what is the source of water, mineral, electricity, anything can be put in, and that many students have done some amount of work. I think, as pointed out in the beginning, although this circuit design and simulation marathon, the word is marathon. So marathon is a long distance running. So यहाँ जो आ रहे हैं लंबे रेस के घोड़े चाहिए हमको, ये छोटे रेस के नहीं चलेंगे. So although the program itself is of 2 weeks duration, we want all the students who are associated to continue to create such circuit design. And that's what we want in that Mapathon. Whoever participated, I think we keep giving appeal to them that whatever work you did, whatever you understood, that open source software, continue to use it, and at least each student starts saying that this is my district and I want to create entire resources of this district available for the entire country. I'm sure it's not a big task. We have nearly 70, 80 lakh students in the technical colleges. And there are also students from other domains. So totally in higher education, 3.5 crore. And these are so simple that it is not necessary that they should be engineering college students. One can be even an arts, commerce college student. It's very easy to learn. You need passion. That passion is what drives all of us. And I'm sure Kannan is a great motivator. He drives that passion. We also had a similar hackathon, which is again, you mentioned Scilab as part of the NMICT, equivalent of that MATLAB, which is Scilab, which is in the open source. There was a toolbox making hackathon, and we got some new tools designed. So all of this is certainly possible, provided we start interacting with our faculty and students. And my few of the other things which we have done, I would like to mention. In this pandemic year, we trained faculty members through what is known as Ghdl Academy, AICT's Training and Learning Academy, in all emerging areas like AI, IoT, machine learning, deep learning, robotics, 3D printing, cloud computing, cyber security, data analytics. 1.65 lakh teachers were trained in this 1 year, 948 5-day workshops. And this has become a world record. We also had a very recently, last month itself, a record, an IIT Madras startup, BUVI, and ourselves, AICT, we jointly held a 1-day intervention of students registering and doing it, training them in Python, and using AI, they will create a face recognition small tool. And 1.26 lakh students did it. Our target was 10 lakh, 6 lakh students only registered, but 1.26 lakh students completed in 24 hours. I think these are all magical figures. The world is looking at India, So how is it possible? We said we have a huge population. So even if 5% of them do something, it is going to be phenomenal compared to the entire globe. And that is the power of using technology on one side and the passion on the other side. I think this is the marriage of the two, and that is creating these wonders. The applications of all this circuit design, I don't want to tell because you are all well-versed. You all know whether it is our basic need in agriculture. You can have robots, you can have drones. Their circuit designs, you can do it at your home and then start operating. Healthcare, you have in education also, you can use aerospace industry. The time that is available has to be fruitfully used. This number 3,000, we will certainly make it 30,000. We will make it 3 lakh. That is the confidence which I have, and we will continuously engage with each other and try to develop this as an open source movement, which we already are doing. Our own MOOCs courses, your spoken tutorials, each one of them are empowering our citizenry at nooks and corners. And the only government that it has to do is to lay the fiber optic line to all nooks and corners, like we reached every village in terms of electricity a couple of years ago. You need to have the bandwidth available at every doorstep, like electricity is available. And wherever the students are not able to buy, we should provide them free devices. And these are not very cheap devices. Government can easily afford. If we do that, therefore, we will be able to truly have access, equity, all of that, whatever we say in our new education policy and everywhere can be truly implemented, and we will see India rising star. All that, what we say, Vishwa Guru and all that is certainly possible. And you are the makers. We are all gray hair people, gray beard and gray hair. We're all losing people, So you are the young generation who will make it happen. Hopefully we will live to see that day. Thank you very much. Namaskar.
Thank you so much, sir. Thank you so much for your kind words. So AICT and Anil sir have always been, supporting our FOSSEE and the initiatives which we do. So thank you so much, sir. Thank you so much. Sir, can you please stop presenting?
Hello, sir. Can you give me permission?
Yeah, you can share actually.
Okay. Yeah, thank you. So now, moving forward, may I please invite Mr. Ganesh Venkataramanan to address the participants. So Mr. Ganesh is a Senior Director of Autopilot Hardware Design at Tesla. So, sir, can you please address the participants, sir?
If I can add a few words about Ganesh, because I got to, in fact, I thought of him only a little while ago and requested whether he could come and talk to the people, talk to the students and motivate. Ganesh was a gold medalist in his BE from Ramravadik, Mumbai University. And then he worked at AMD for many years. And he was an engineering director. He led several processors, microprocessors design. Now he's one of the people who founded the microprocessor division at Tesla. And Tesla electric cars, you're all familiar with. So we are really, really delighted to have Ganesh with us. Ganesh, please go ahead.
Sure. Thank you. Thank you, Professor Kannan. Thanks, Yash, Kunal, and Dr. Saraswati. Pretty honored to talk to all of the young participants here. Somehow I feel like I should go back in time and actually relive my student days right now with the kind of facilities, the kind of work that is going on. During my days, I did my master's after my bachelor's from Bombay University at IIT Delhi in the field of integrated electronics. And it used to be, for the master students, we had to share a PC with PhD folks, and we would get like 2 hours a week. That was the maximum we could get. And then all of this work that you're doing in open source, I could only have, I couldn't have imagined in my wildest dream that it will be possible. And it's so delighted to see that the amount of work that is going on in the open source, that's the foundation. So you have a lot of tools, resources available. The one part which defines success in my viewpoint is the curiosity that a student has. The more curious you are, the more you'll explore. You will fail on many things, but you will learn from it. the next time around you won't fail the same way. That's how I learned these circuit design tools to simulate even the simplest things. Some people question, like, why should we go through this? This is your foundation. Like I still have used many of those same foundational aspects to date in my job. And it's so fundamental in what we do in design, and we don't realize when we are young going through this as to how it'll come in use. But all I want you all to remember is, if you're curious, start building, start hacking few things, you will learn, and that's it. Keep continuing that curiosity. That's the best formula for success. And with these kind of tools available, I feel it's a new era where innovation will start up front. It won't wait for folks to learn in their job. Like by the time you graduate from your respective colleges, you would have acquired a lot of the skills that industry is looking for. And then I would just say, a lot of what I saw in the eSim package can be put to use today. I mean, when the pandemic hit, I was involved in a project at Tesla to create some of the medical equipments needed here in US, and including respiratory devices and many small things, even small things that people were struggling with, is an alarm system if something goes wrong in a hospital. So right now, with what India has gone through, hopefully everything will go back to normal pretty soon. But these are the tools, these are the things which will come handy no matter where you are. This is the skill set you can use either in your day-to-day job or in order to help in a crisis. I mean, these things will come handy in many different situations, many different scenarios. And that's where the fundamentals that it will teach you, the curiosity that you have, the combination of that is a great formula for success. So please keep that going. Be curious, develop as many things. Some things are simple, but just reinforces what is right, what is wrong in terms of the simplest things. You build upon that and build the next complex thing and the next complex thing. So that's the best formula for all of you. And I'm pretty delighted. Like, I would personally like to see how this effort goes, because these circuits, they are the key for innovation. Even though the abstraction levels of GHDL and other aspects are there, but it starts from very basic things. My father, who was a electronics professor also, he said the functional aspects of device does not change, be it vacuum tubes, be it bipolar devices, be it CMOS, next will be quantum devices. That fundamental aspect of the device doesn't change. And this is a perfect tool to teach you the fundamentals. So keep that curiosity going. Thank you.
Thanks, Ganesh.
Thanks.
Thank you so much. So next time, whenever we see any autopilot or driverless car, we know that Mr. Ganesh is one of the important people behind it. Thank you so much, sir. Thank you so much. So moving ahead, let us now welcome our partners who have been our partners for this marathon. So first, I would like to invite Mr. Kunal Ghosh, who is the co-founder of VLSI System Design Corp Private Limited, and Kunal is also an IITB alumni. Kunal, over to you.
Yeah, thanks, Yash, for that great introduction. Let me share my screen. All right, so my talk will be focused on education itself because I've been into this field for like 10 years now. And so my title is quite simple. It's eSIM, a very powerful tool for the electronics engineering education. And now in the next 5 minutes, I'm going to share some data, some real-time data based on eSIM, and that's how you would realize that if what I'm saying over here as why am I saying that eSIM is a powerful tool for the electronics engineering education. So my background is I've worked I got placed in Qualcomm in 2010, and after Qualcomm, I got my design experience over there. After that, I joined Cadence as an application engineer. So I have the CAD experience as well. And then I founded my own company, which mostly focuses on open source VLSI design. So I have used almost all the tools, almost all the industry tools which I have been working on. I've worked on most of the tools. What I found, how I found eSIM different than others is that eSIM is it's like a one-stop shop for all the open source tools. For example, if I want to do PCB layout and generate the Gerber files, if I want to do a circuit design simulation, which currently which is this marathon all about, if I want to do a mixed signal simulation and analysis. So I have to right now I have to go to three different vendors, three different tools in the commercial space. But what my students have been doing some projects with my students, what they have come back with me saying that eSIM is like one open source tool for all of them, and they have experienced this from their own IP design project. So that is one thing. Second thing, VSD ourselves has developed at their own university. It's basically not the regular university. It's basically a curriculum which is complementary to the existing electronics engineering. So all of the courses that you see over here, it's basically spread across 8 semesters, and we are almost covering from board design to the IP design and everything. And if you look over here, almost 60% of the electronics engineering can be covered just by eSIM. So what does that mean to us? Let's say we have 1 lakh teachers across the country, and if every teacher handles 20 students, we got like 20 lakh students, and all these 20 lakh students can get uplifted in all these topics which I've highlighted just by one tool, just by eSIM. And I have live I have live data from the students itself who have actually used eSIM and built things with the eSIM circuit design tool. And of course, we have gone till the further stages also, where we have built IPs using the circuits for built using eSIM, and the layouts were done using another open source tool. But on an average, if you look into the entire open source world, 60% of that can easily be covered by the circuit simulator tool, which has been developed by FOSSEE IIT Bombay. And now with this particular marathon, what we are trying to do is we are taking the eSIM tool, and we are trying to connect the 130 nanometer real foundry. So till now we have been using the foundry data which was not real, and now for the first time we are going to use real foundry data which is from Skywater technology. So we are actually in a very good space where luckily we have got the Google who has basically sponsored Skywater technology to open up or open source their 130 nanometer technology node. It's a real technology node where you can build IPs and actually manufacture those chips for free, or almost for the free of cost, or by some alumni sponsors. So all of that can be done. So this particular marathon, in the next 2 weeks, whatever you build, just take it from us that you're building something real. It's not fictional, it's not curriculum, but it is something which you can actually see working on a real chip. And that's the vision, and that's where we want a lot of circuits to come out of this one. Once you build a circuit, VSD can help you to get to the layout phase, and probably we can look for some alumni funds or some funds to get it taped out and get a real chip and package and get a real chip. That's the vision. And the reason I'm pretty confident about this one is because I have done that in the past. If I introduce myself, my name is Kunal Ghosh. I have done my master's from IIT Bombay. Post that, I've led a team of SoC design at Qualcomm, and I've been working from 40 nanometer to 16 nanometer test chips. Then I joined Cadence as a lead technical AE, where I deployed Cadence backend SoC design products and almost 18 customers. And I've worked till 7 nanometer technology node. And the important thing that our company has been doing for last 10 years is that we have trained trained close to 35,000 plus users across 141 plus countries, and they have built close to 40 plus analog IPs, where circuit design part was actually done using the eSim tool, and we are going to demo that at the end of this particular webinar. So that's why I'm pretty confident about the future, and I'm pretty confident that all of you who have participated or who have joined yourself as a part of the registered yourself as a part of the marathon. There are a lot of things that you can actually achieve, because I have seen that firsthand happening. And that's all. That's the introduction about myself. And if I am allowed to show you some of the work that our students have done, I can show you the list of IPs that our interns have built only using open source CDA tools. So if you look over here, the universities is from NIT Warangal, from Arizona State University, from Germany, Munich, from Oregon, United States, Triple ITDM, Kanchipuram. So if you see the list of colleges across the world who have participated building hardcore real IPs using the circuit simulator tool that we're talking about, that's huge. And this can be easily scaled up to the number of students that we target to. And if I can show you one of the work of one of our students, you can see how beautifully he has basically used eSIM and documented it in the nice way. And all the simulations was done purely on the eSIM part. And that's where we contacted Professor Kannan about how do we scale it up to a larger mass, because we definitely see a good potential over here. If you can see, this circuits for all built by a student, and he's like a third year student. So if a third year student can build great things that you see on my screen, all of you are mostly in the second year, third year, or maybe in the final year, or PhD students. You can build even greater things if you join hands together. So that's the idea, that's the vision that we have set for all of you. So I would encourage all of you to give your whole heart to this particular marathon. All of you have that thing in you, and me and Yash and Saurabh and the entire FOSSI team, we're all there on the Slack channel to help you with all the kinds of documentation that you need. So yeah, all the best, and you will hear a lot from me during the course of the next 2 weeks during the hackathon. So yeah, thanks Yash for allowing me to speak, and thanks FOSSI team for the entire platform that we have set up for the eSIM marathon. Thank you, Professor Kannan, and thanks, Yash.
Thank you.
If I can add, we are delighted to have Kunal Ghosh, Anaga Ghosh from VSD joining hands with us in organizing this. Their role is going to be important to evaluate all the submissions, okay? Because they have a lot of experience in using eSIM. And then the students, that people will be contributing, their circuits are to be assessed. They have written a script and so on. So in fact, it is scalable. Thank you, Kunal, for joining hands with us. Yeah.
Thank you. Yes, thank you. Thank you, Kunal. So now, moving forward, I would like to invite Professor Madhav Desai to address the participants. Professor Desai is a faculty at the Department of Electrical Engineering, IIT Bombay. He'll be explaining, what exactly does designing an electronic circuit mean. So over to you, sir.
Yeah, thank you. Thanks for inviting me. And can I share my screen?
Yes, sir.
Yeah, because I'll just draw a few diagrams.
Okay.
Since we are doing circuits, diagrams are very important.
Yes.
One second.
Sure.
Okay. Share screen. Yeah. Okay, can you see my screen?
Yes, sir.
Okay, so I yesterday Kunal called me up, and yesterday or day before, to talk about talk to this group of students who would be designing all kinds of circuits, from what he told me, right? From
Yes.
analog, digital, mixed signal. It's a wide range of circuits. And I think so. Instead of speaking about analog or mixed signal or whatever, what I thought was a good idea was to sort of uh, give you my thoughts on what does it mean to design a circuit. Yeah, what does it mean? So if you ask that question, so first thing is, before you design the circuit, right? I mean, you have to have an idea where you are headed, right? Like you have to ask some basic questions, right? Say, why are you designing it? What is its specification? Who will use it? How will they use it? Yes. And how good, how shall I say, how dependable do you want it to be? See, all these questions are very important. For example, let's say why. For example, each of you who's going to be designing a circuit in this uh, exercise will have a goal as to why you want to design that circuit. It obviously, since you are students, it's part of your education, and you expect to build up skills and towards becoming part of the technology ecosystem later on. So you are really, for most of you, the why is, you want to learn something, right? Okay, then the question becomes, then what are you going to build? Like, what is the specification? For example, let us say I want to build an amplifier, analog amplifier with so what are the specifications you want to build? For example, the gain, bandwidth, right? Input impedance, output impedance. These are the things that you for sort of, here's where your theoretical, how shall I say, understanding comes into the picture, right? Because if I ask you what is an amplifier, and I tell you, specify an amplifier for me, well, you need to have some reasonable understanding of what an amplifier is. So you need to understand what it means, what it does, what does it mean, the gain of the amplifier, the bandwidth of the amplifier, the input impedance, output impedance. And you can go further. That's why I put a dot, dot, dot. An amplifier eventually can get quite sophisticated. People do their PhDs in design of amplifiers. So it can be something quite simple. It can be something quite complicated, depending on your theoretical understanding. And obviously, you got to start somewhere. So my point here is that when you design a circuit, or you put a circuit together, of course it's an activity, but that activity has to have some meaning. And that meaning is answered, meaning the first question is why, right? I mean, why? And then what? That is a specification. Then we ask the next question, which is who will use it? For example, will anybody use it? Will you use it? Will nobody use it? This is important because if nobody's going to use it, what is your motivation for putting it together? There should be at least one person who will use it. That's yourself, right? And of course, how will you use it? For example, let's say you design an amplifier. What does it mean you will use it? You will use it for the purpose why you are designing it. For example, for learning. Yes? Let's say you design an amplifier, you will use it to help you learn about electronic circuits. And that's where, this simulator comes into the picture, like this eSim that you've been hearing about. So you may not be able to realize a 130 nanometer circuit today, but you will be able to design it. You will be able to simulate it. and you will be able to fulfill the purpose, which was to learn. So you put something together, you build an amplifier. It is important to simulate it so you get the feeling that it worked. Yeah. Okay, and so that this who will use it is of course linked to how will they use it. Yeah. So for example, let us say you design something, an amplifier. Now you design it in, let us say, CMOS technology with a certain gain, a bandwidth, input output impedance requirements, and you want to confirm that the thing actually worked. If it worked, well, your confidence goes higher, and you can go on to the next level of amplifier design, right? So basically what I'm trying to say is that, you have this theory and there is practice, and the two are interactive in the sense you learn a bit, do a bit. When you do a bit, you learn, you go back and learn a bit more. You go back and do a bit more, learn a bit more, and that's how you actually build up your knowledge in any field. And here the simulator is of course of great importance, because whatever you build, you may not be able to afford to construct it today. Maybe 10 years, 3 years from now, 5 years from now, in a laboratory you might have access to but you can use a simulator to sort of give yourself feedback as to whether you have really solved the problem or not. Yeah. So that's so you need to sort of, my suggestion is, you need to have these big things, this big picture very clear in your head. Now second, once you're clear why you're doing it, what you're going to build, how you're going to use it, etc., then the question is the process of design. Now there are some common things in the process of design. So what is in the process of design? As I mentioned, after you have answered the basic question, you have a specification. As I tried to give a specification for the amplifier here, but in general, you'll have a specification. I think I'm going to design something which looks like this. It's supposed to do this, and this is absolutely important, because if you don't write a specification, your design is futile. I mean, your design will have no shape. So you have a specification, and then you have a realization or implementation, right? Now that realization in an amplifier, you have to basically select the topology of the amplifier. You'll have to size the transistors. You'll have to, how shall I say, work out, what the variation in its performance could be if the transistors are not perfect, right? Or not identical. So you have to worry about matching and stuff like that, especially in CMOS design. So anyway, you realize it. Now, after you realize it, well, you have to verify it. Yes, you have designed it. Now you need to verify it. How are you going to verify that your design is correct? Okay, you did some paper calculations, you put something together, and you have a good understanding of the theory, but the devices that you are actually using are not the same as the devices that you use in your theory. There are differences. So how to verify? Well, simulate. Yes. You realize, you verify. If the your circuit is not achieving its goals, then you need to go back and change your realization. Yes. Or maybe you give up. You say it's not possible. You go back and change the specification. Yeah. So these three steps are of great importance, and the simulator plays an extremely critical role in closing the design process, because you can't just go and manufacture a chip of something you designed and then see if it works. You have to have a pretty clear idea that it's going to work when you actually build it. Okay. So this is so you need to sort of keep this chain in your mind. And one more thing I want to sort of point out to most students, they are very poor at a very important thing, which is called documentation. So when you say I'm going to build this, you should be able to write a specification which a normal person can understand. When you go through a realization process, you should document that realization process, saying here are the decisions I made. I chose this transistor size to be so and so for this reason. Yeah, so that entire realization process, you need to have it documented. Now, by document, you don't mean you don't have to write a big encyclopedia or a novel. You need to put down enough information so that another person can figure out what you have done. So this is called review. Whenever you work for a company or anywhere else, whatever work you do is going to be reviewed by somebody else. As a student, your work is reviewed by your teacher. Now, without documentation, there can be no review. And without review, there can be no growth, because these are absolutely critical processes in the design process. So what I'm trying to say is that this is general. This is general for design. You have to answer the big questions. You have to capture a specification. You have to go through a realization based on your fundas. Then that realization has to be verified. In our world, in the circuit world, you verify it using a simulator. And not only that, during this process, you have to continuously have a clear picture captured in your documentation so that it can be reviewed. Okay, so I think that's, if any of these pieces is missing in practice, for example, if you don't have documentation, nobody is going to use your work. If you did not get it reviewed, it's unlikely you'll have a good realization. If you did not verify it, it is pointless anyway. Your circuit is guaranteed not to be correct, almost surely, unless you have copied it from somebody. So, you need to sort of take the design process as an integrated problem, so that what you do will achieve its goal. Okay, so I think that's all I had to say. Yeah.
Yeah, that was quite very simply explained. And Yash, I think we are on the right track, where we have asked people to do the literature survey first,
Yes.
so that they document the entire thing, and that entire thing is there on the website. That was very nicely explained, sir.
Thank you so much, sir. Thank you so much, sir.
Okay,
So,
thank you, Kunal. Thanks for inviting me. Okay, I'll sign off. Huh,
yeah,
Kunal?
sure. Thank you. Yes, sure, sir. Thank you.
Thank you, sir. So, may I now invite Professor Jayanta Mukherjee to address the participants. Professor Mukherjee is a faculty at the Department of Electrical Engineering, IIT Bombay, and he'll be talking on RF circuit design. Over to you, sir.
Sir, you're muted.
Good morning. Thank you for inviting me to this presentation. So as I understand, this is a presentation on eSim, which is an open source software. So my work in VLSI involves RF circuits. So what are RF circuits actually? So RF circuits are ubiquitous nowadays. Any mobile device, any device, laptop, even laptops, Wi-Fi, which use Wi-Fi or cellular network. And then with the upcoming 5G devices. So here, the circuits that are designed, they are most often designed in VLSI, except for some portions like the power amplifiers, which are external. And of course, the antennas are also external. So my work encompasses this part, this communication hardware of any device, whether it's 4G, 5G, or maybe future generations of hardware. Now, what makes these hardware unique over other components? So VLSI, there are various, it can be classified into various groups. One is digital, then there is analog, and then there is this RF. So RF is basically high frequency, and we have to go to high frequency because the advantages that higher frequency offers, the microwave range and the millimeter wave range offers. And in 5G, there is a focus towards going to the millimeter wave range, which is the even higher range, like 30 gigahertz or something like that. Most of the 4G or 3G standards are within 6 gigahertz. So when you go to such high frequencies, the considerations that you have to take into account while design are quite different, because as the frequency increases, there's something called parasitics. So parasitics are they degrade the performance of a circuit. So, and these parasitics become more prominent at higher frequencies. So at lower frequencies, for example, at kilohertz or megahertz, these are not so significant. But in gigahertz or tens of gigahertz, these become significant. One other difference in radio frequency or this RF VLSI design is the unique nature of problems that devices in these frequencies face. For example, linearity of a circuit is very important. So just to maintain the linearity, because if the circuit is not linear, then you will have a lot of distortions. Your quality of the call or the internet connection, data rates will decrease. So linearity is an important issue. Then efficiency. Efficiency is another important issue, because efficiency determines how long your battery will last. So if you have a very power consuming device, then your battery will drain quickly. So, and nowadays we want to charge as little as possible and hope that our devices work for as long as possible. So these are some issues which are unique to these categories. Now, even though I said the communication hardware for these 4G and 5G are mostly in VLSI, but not everything can be done in VLSI. For example, there is something called a power amplifier in a RF circuits, which basically amplifies the output, this input signal from the baseband to the antenna in the transmitter. So since the power amplifier operates at a higher power range, we usually go for gallium arsenide or gallium nitride based circuits. Whereas for the baseband part, we go mostly for CMOS based PLSI. Now, how do we do that, and how do we test it? How do we design it? So for the VLSI circuits, we do it the standard way, the same way that we do any other VLSI circuits. Of course, as I mentioned, the parameters are different. For example, in analog or digital circuits, linearity, then efficiency, these are not so important, but here these are important. Then what are the tools that we use? So mostly for RF design, I personally prefer Cadence, and the simulator of choice is Spectre RF. And then for the power amplifier design, we use tools like ADS. Now, I understand that this seminar is on open source tools, and I hope that the open source tools are able to incorporate the models of the transistors. Now, what happens is in any VLSI or any circuit design project, you need to have a very good idea about how the transistors that you will be fabricating or will be using in your circuit, how they work. So for these, there are something called standard models. One of them is a famous Berkeley eSim 3 model. Now, these models have to be accurate. Unless these are accurate, you cannot actually design them or fabricate them. So now so far, what I've seen is that tools like Cadence, they have good industry interface, and many of the design fabrication processes or fabrication units, they produce models which are compatible with this Cadence and ADS. So I hope that this eSim simulator that we are discussing here is also able to incorporate these models successfully. So that, because one thing I would like to say that these proprietary software like Cadence, these are very expensive actually. So if there is an open source alternative, that would be very nice. And So that's the design part. And then we send it to fabrication, these circuits to some foundry. For example, I have mostly worked with UMC Taiwan. And after getting back the circuits, we test them. Now, testing is another problem at RF circuits. In fact, testing takes more time than design. That I want to emphasize. Because RF circuits have to be tested with a lot of care, because as I said, the parasitics matter. So even if you touch the circuit while it's operating, the performance can change. And often we need to reiterate the circuit. So something works good, but it often happens that we first say we get a chip, or we design some circuit using some standard gallium nitride or gallium arsenide. In 90% cases, it doesn't work in the first iteration. So then we have to again make the PCB board, again send it for testing. And then there is also something called best testing. Best testing means that you leave the device or your circuit to operate maybe for days, and then use some kind of software to extract the best results that you get. So that is another time-consuming process. So overall, I have seen, testing of RF circuits is actually takes more time. So, and by more time, I mean sometimes it can take 1 year actually to test. So that is a very important part, and so for that we need good equipment also. So that is another thing that you have to keep in mind that before designing, that how you will test. Sometimes you have to design based on what test equipment you have. So even while designing the circuit, you have to be aware of how you will test it, and then your layout or other features of your circuit need to be modified based on what kind of test facilities you have. So I don't want to go into details. For example, when you test a chip, on chip, sometimes you don't even make a PCB. You just take the wafer from the fabric, from the foundry, and do something called a direct on-chip testing. So for direct on-chip testing, the probes that you have in your lab should match with what you are actually sending for layout. So these are another important feature. So that's all I wanted to say about RF testing. It's challenging, but it's also interesting, because one good thing about RF circuit design is that it's always in demand. It's always in demand because these communication standards keep changing, isn't it? 2G, 3G, 4G, 5G, then there will be 6G. And every time there is a new communication standard, there is a demand for a completely new set of hardware and a completely new set of circuits. So this demand will keep on there. So that is one advantage of RF design. Any questions?
Thanks. Participants, if you have any questions, you can drop it in the chat box. But thanks, sir, for showing everyone the vision of the circuits. Definitely, RF is the one that we want all of them to reach one day. But yeah, this is a good start for all this all the students. Yes, over to you, Josh.
Thank you so much, sir. Thank you so much. So we have heard the views on circuit designing from the academic experts. Now just let us also hear the views from industry people. So I would now like to invite Mr. Ripen Tiku, who is the Chief Executive of Powai Labs. Interestingly, he is also an alumni of IIT Bombay. So over to you, Mr. Ripen Tiku.
Thank you for inviting me. I'll be very brief.
If I can interrupt a little bit. So I want to thank Powai Labs. I want to thank Mr. Ripen Tiku and Professor Madhav Desai for, as I already mentioned, giving us the technology to have mixed signal simulation in eSim. So we are planning to do a lot of work with Powai Labs. We are pleased to have Mr. Ripen Tiku here. Ripen, please go ahead.
Thank you, Professor Kunal. So I would like to reiterate here that we are trying to build design engineers. So the tools, as a design engineer, you are more or less agnostic to the tools that are being used. You are not kind of trying to be a tool specific technical person. So you're basically trying to be a design engineer. So fundamentally, this is agnostic to the work you want to do. So that was one part of it. There were two topics I want to cover. One was to kind of emphasize that while you're working on open source tools, don't feel any inadequacy with what you are trying to build. This is good enough to learn and kind of move from here to the industry to build your careers or build enterprises of your own. Coming back to what little while back some of the academic people brought to the notice, that we have to have an idea as to what we want to build. As a design engineer, you decide on what you want to design. But you could kind of, this whole work while you're kind of doing some initial designs, where you are kind of trying to pick up the whole technical ambit in terms of designing, you can also slowly do more in-depth. This can be very like, I personally, my final year project turned out to be a company finally. So you could kind of take this a little bit more ahead and do more in-depth analysis of what you are trying to build, and this idea that you have, that IP that you want to design, you could kind of understand what are the equivalent IPs available. Can you make a differential, some incremental improvement in that? Can that be a disruption in the marketplace? If you do these preliminary, this is part of the research. I'm not talking about purely engineering research, or this is about understanding the marketplace and picking up these inputs. This is very important to build something of great value. And many big enterprises that we see around the world, they have started like this, with a small idea, where they thought that this idea can bring certain value to bridge a gap that's already existing in the ecosystem. I think some of the speakers before me emphasize, I think, presentation and communication skills. This is something that is completely amiss with many of us. So, because you should be able to communicate what you are trying to build, you should be able to document it, you should be able to write it before you start building it, or before you try to understand its impact or what value it brings, and you should be able to write. Writing is the first step in the direction of building something. So, and communications, you'll have to go and make a presentation to people. You would have to articulate what you intend to build. Whether you are in an academic environment, you will have to still tell your professor what you want to do, or if you're taking this idea out to the industry, or if you're trying to build an enterprise around it, a startup, you should be able to communicate yourself very well on this. Then you should be able to pick up the industry input and feedback on what you want to build. Is it really something important, that, or is it because I would say that if you're getting 100 such ideas in your head that this is worthwhile to pursue, so maybe one or two would be really what would stay back with you. You have to keep your ears to the ground and arrive at what you want to drive forward. So very important. You have to keep on bouncing what you want to build with the industry, gather that feedback. Are people really finding it valuable? Here, I would also put a word of caution. Many a times, it's not necessary that industry, great product or great engineering will happen purely from the feedback of the industry. I think you will have to first arrive at what you want to build and fine tune it from a perspective of the user, from the perspective of the industry. That is something. And then there would be a product engineering, so that you make it more user friendly, all those interfaces that you want to apply to it. So that's like part of the product engineering that you would have to take forward and build a prototype finally. The most important part is that whatever IP, like sometime back, one of the professors before me was talking about an amplifier. Now, if you think that you're building an IP which would have all those technological advantages, you can build a prototype, get it, and take it to an environment where it has to work, and do an alpha and a beta testing of that. And based on the feedback that you have, you improve on your IP. And your next release would be based on your feedback that you have captured. So this is a iterative process where you take the feedback from the environment where you deployed your IP and improvise on what you have till you finally arrive at something that, yes, this is now my first version of what I want to provide in the marketplace. And you have to have proper documentation so that the party which is taking it from you can use it very easily. From here on, you have three choices. One is to license it to an industry and get a royalty and technology know-how fee, or like a very simple, that's predominantly what academic institutes do. They license their IP that they build within the academic. That's one model you could also do, employ. The other is finding a job relevant to your project, because you would be in very high demand based on this IP that you've developed, and the companies which are trying to work in that domain or are using that IP in their larger system that they are building. You have a very good chance of finding your employment there. Third would be a startup. That would be like another journey you could take. These are the three options you have based on what you have built, what you have decided to build. Then from there onwards, startup can be high technology entrepreneurship. This is very different from the startups that we see predominantly in our country. The startups that we see are basically a replica of a successful startup that has been built in North America, Europe, or other parts of the world. And India as a big market, can they two of them integrate? So those are called unicorn, and those are like, media is full of those big stories. But here you are talking about a high technology enterprises when you really do some engineering and solve a problem through engineering. And very few companies like this have come out of India, but you are on that path and you can really go in that direction. Then drawing a business plan is very important as to what your costs will be, how many people you will employ, what salaries. So building a business plan for what you are offering. And this business plan has to then be taken forward with the people who will fund you. And before you build a business plan, you should have a team in place. People with diverse skill sets so that you could converge together and build an enterprise. Somebody who's very good with sales and management and marketing, or somebody who's very good with innovation, or third guy who's very good with raising funds. So that kind of a diverse, symbiotic team will finally be able to build an enterprise. Then most important is to acquire a customer, somebody who is ready to pay you for that IP. This is the most toughest part. Till here it's all very romantic and everybody till here wants to be an entrepreneur. But from here, this is the toughest part to basically, if you're able to make a sale and somebody is ready to pay what you build, that's the first litmus test that you have arrived. And then you could look at different funding options. Do you want to do a venture fund, sell your equity? Do you want to raise debt? Those are different options which you could, and kind of take it, this whole thing which I've just articulated in the form of project. So that's all I had to say here, though this is very different from what my predecessor spoke here. Thank you very much for listening to me. Thank you so very much for inviting me.
Thanks, Ripan.
Thank you, thank you very much, sir. Yes. So now moving ahead, may I just ask Professor Kannan to wish all the participants for the marathon, sir? Can you please do that?
Yeah, so really delighted to have you all here once again. I wish you all the best. I can tell you that you are in safe hands. We have a crack team that is going to help you. And our intention is to help every one of you to complete the work. Okay? Because we do have an ulterior motive. We want to collect all the designs that you create. We want to display them to the whole world, saying that our students from such and such university, such and such college have created such amazing thing. We want to showcase your work to the whole world. Okay? So will you please help us do that? We want all of you to take interest. It's going to be very important because all the people who talked about earlier mentioned that this is very important activity. So I would want you to take seriously. Don't hesitate to take any help, but put all your best. Wish you all the best. Thank you.
Thank you so much, sir. So we are towards the end of this inaugural ceremony. I would now like to invite Ms. Usha Vishwanathan, Senior Project Manager of FOSSEE Project, to give a formal vote of thanks. Usha, I'm over to you. Yes, a little feeble.
Yeah, thank you, Yash. Thank you everyone for attending this virtual inaugural ceremony of the Circuit Design and Simulation Marathon using eSim. I would like to thank all the special dignitaries who were present in this event. Professor Anil Sahasrabudhe, Chairman AICTE, Mr. Ganesh Venkatramanan from Tesla, Professor Madhav Desai and Professor Jayanta Mukherjee from the Department of Electrical Engineering, IIT Bombay, and Mr. Ripan Tikku from the Powai Labs. I would also like to thank our partners, VSD and AICTE, for supporting us in this marathon. A special thanks to our funding agency, Ministry of Education, Government of India. I would also like to thank Professor Kannan Maudgalya, who is the PI of our project and who is the driving force behind this marathon. Last but not the least, I would like to thank all the team members of the FOSSEE project who are actually tirelessly working for this marathon. I also want to wish all the participants very best for this marathon. And I also have an announcement to make for guiding the participants on how to do their project in this marathon. We have arranged a session on 10-bit DAC IP design using eSIM and Sky 130 PDK. So I will ask Kunal to take over, who will be actually presenting that session. Thank you. Thank you all.
Thank you. Thanks, Usha ma'am. So yes, now we have done with the orientation, and we are going to quickly start a webinar, which is completely technical, where all of you will be seeing how whatever the speakers have spoke in the beginning, how a student has realized this entire thing right from scratch, right from specifications till circuit design till layout, the entire thing, entire flow. Whatever he has done, we are going to display that very shortly. So does anybody need a quick break, or is it okay? Do we continue with the webinar? Does anybody need a quick 5 minutes break? I can continue for 5 hours more, but you can continue.
Yeah.
How about others? Just type yes if you want me to continue.
Break.
Okay, so maximum people are saying yes.
Yes.
All right, so people need a. Okay, so what we'll do is we'll take just quick 5 minutes break. You can just go back, stretch your legs, and have some water and snacks next to you. We are not going to disconnect this link, and we'll continue on this link itself in another 5 minutes. So it's 12:27. We'll come back in 12:35. Okay, that's enough break for all of you. And in the meantime, I will show you. I'll just run a video for all of you. That should give you a good amount of motivation of what students can do. So watch this one.
Hello everyone. I am Praharsha Mahurkar, and I'll be taking you through mixed signal SoC design today. Okay, so we've seen it. All of them we have covered. All of them we have converted. All of them into pins. We'll take a closer look over here. We have got a bounding box to the middle of the power rail, and also the top power rail, the middle of the top power rail. So we have got it. So now that we have dumped out our left file, the left file is ready to be used in the open lane flow. Now next, apart from this, I also need to run the Docker. The Docker command is this. So we need to completely copy and paste as it is. So that comes to the end, the final layout stage. That is the final output which we require. Output. So let's see all of these stages in the open lane flow using inside the demo. And I hope you have understood exactly what we need to do, and you've understood the tips for doing the mixed signal flow. Hope you have enjoyed the session, and happy learning. Thank you.
Hi everyone, I'm Shon Taure, and I'm going to drive you through the configuration of OpenRAM for SRAM design using Sky 130. So the next figure shows a 2x2 array. Similarly, for a 4x4 memory cell, we need to replicate the 1-bit SRAM cell for 16 times. It is designed by cross-coupling two CMOS inverters, which hold the bit and the two access transistors for enabling the access to the cross-coupled inverters. This circuit is a combination of two D latches. The first one is a negative level sensitive latch and the second one is the positive level sensitive latch. These are the two cross-coupled inverters and the below two NMOS are the access transistors. Same goes with the M1, M2 and M3 stack. M1 connects M2 through the VR1, M2 connects M3 through the VR2 and M3 connects M4 through the VR3. We can see the 32 cross 1024 memory array. Let's zoom in. We can see the arrangement of the SRAM cells, the dummy and replica cells. If we zoom at the SRAM cell array, we can see that the DRC errors are now gone. The detailed configuration files and the documents can be found at the Git repository mentioned. Thank you and happy learning.
Hello, I am Anmol Purti and I welcome you all to this webinar. This can be avoided by using a startup circuit. The startup circuit along with the BGR circuit is shown in this diagram. We will be using the formula alpha 1 slope of PTAT plus slope of CTAT is equal to 0. Now we can see here that our V reference is having characteristic more like a PTAT. The slope of CTAT we will find by clicking the left mouse button at 40 and while pressing it we'll bring it to 60 and we'll leave it. The contacts that we'll use for this resistor are X poly contact. We'll press the mouse middle button. So from the circuit we can see the gates of XM1, XM2 and XM3 are connected. So we will connect them using the polysilicon layer. We have to make the contact here from the resistor to the metal. But here we have forgot to put the substrate terminal of NMOS. We will do this now. I would also like to thank all the people who have helped me directly or indirectly. And I wish you all the best for your future. And thank you for attending this webinar.
I'll be covering the design of comparator IP using Sky 130 PDK. Okay, so this looks good. And now we can get into the details of the circuit. So here we get the simulation output. The blue is the enable signal, that there are two different levels at which the voltage changes from 0 to 3.3, so signifying that there is a hysteresis present and how much it is at 10 microampere. We have a positive input, we have a negative input. These are the differential inputs. We have a IHIST, which is this is the M5 transistor. These two are our feedback transistors here, M6 and M8. We will have to make sure that appropriate metals are used and the signals come in and go out the appropriate way. Thank you.
Hello everyone, this webinar session is about the IP design of potentiometric DAC using SkyWater 130 PDK. So why the scaling network is required is that we will be dividing the entire VREF into some voltage parts basing on the input binary switches. So what does this actually mean to us while designing a circuit is that we should be giving a proper reference voltage to get an output that is stable, that has a proper settling time, and that also has a proper output step response. And yes, now we'll look into just a quick review of the application note for this DAC. This is the first step that we do, since it's a resolution of 10-bit DAC. And this is the first step that we derive from the actual specification. INL, as we have seen, INL is what it is an integration, or it is a sum of all the DNLs that were there till now on the symbol. And now I'll just connect it. So I'll just rename it with the out. The thing that we need to observe here is to insert anything. We do not have a library specific to 130 nanometer, Skywater 130. These are all built-in examples.